Suppose x and y are two jointly distributed random variables. We have combined x and y using some known function h to construct a new random variable z. And we are interested in expected value of z. Now, one technique to find this could be to use the definition directly. Just work out the distribution of z, and z being a univariate random variable, a single random variable, you can apply the general definition to find out expected value of z. But a simpler alternative exists. If z is always non-negative, then expected value of z may be obtained using this formula, where this f is joint density of xy. So this formula is for the case where you have a joint density. Now, since the integrand is non-negative, this is non-negative because of this, and density is always non-negative. So this integral is always bound to exist, though it may be infinite. And in general, that is, if this non-negativity condition is not present, then we can proceed in the usual way. We define z plus and z minus. This takes care of the positive part of z and this takes care of the negative part of z, but both these random variables are actually non-negative. And then we define expected value of z as expected value of z plus minus expected value of z minus, which is the general prescription, and it's natural because we have z equal to z plus minus z minus. This definition is actually a consequence of the general definition of expectation in terms of supremum, etc., that we touched upon in the last semester. I do not expect you to remember all those things right now, but I will just remind you that this is a consequence of that. How this definition comes from that definition will be clear once we learn about Lebesgue integrals near the end of this semester. And incidentally, if this is infinite and that is also infinite, then we say that this is undefined. Now this format, this particular formula is very much similar to the univariate case. Unfortunately, this does not always hold. Even in the univariate case, it does not always hold. One condition when it holds is if it is always non-negative. If it is not non-negative, we have to go into all the hassle of z plus and z minus. But this theorem is going to give you another condition under which also you can use this. And that condition is if absolute value of z has finite expectation. Absolute value of z is non-negative, so its expectation must always exist. It could be finite or it could be infinite. Now, if it is finite, then expectation z is also finite. It could be negative, but it's finite, and we have this thing. Now, this is what we have most of the time. So usually this condition will be satisfied, and so we can find out expectation by just multiplying it with the density and taking integral over the entire space. The proof of this theorem is pretty straightforward. Once you notice that absolute value of z is actually z plus z minus. So if this has a finite expectation, each of them must have finite expectation, and then by doing a little jugglery, you can arrive at this. We shall not pursue the proof here. You can try your hand at it yourself. In this problem, we are starting with xy, which is uniformly distributed over this set S, which is a subset of R2. Your main problem is to find expected value of xy, and these two are basically hints of how to proceed. You should first sketch this set by shading it as a subset of R2. Then you have to find the joint density of xy. Remember, it has a uniform distribution, so joint distribution should be a flat constant surface over S, 0 outside S. You have to find out what is the height of that flat surface, and then you have to use the definition to find expected value of xy. In this case, these are always non-negative, so you can directly use integration.